When people say they want to understand the universe, I always wonder if they realize what they're signing up for. Because the moment you decide to really look at something as tiny as an atom, the universe stops behaving like a well-trained dog and starts acting like a cat that knocks glasses off tables just to see what happens. Let me start with something that sounds completely innocent. Imagine you have a tiny ball, just a little speck. You can picture it, right? A grain of sand, maybe smaller. Now shrink that grain of sand down and down and down until it's so small you can't even imagine it anymore. That's about the size scale we're talking about when we say atom. And naturally, your brain says, okay, got it. Tiny thing. Probably just a smaller version of a big thing. That's the first mistake, a very reasonable mistake. The kind of mistake evolution trained you to make because it works beautifully for coconuts, tigers, and cliffs. But atoms are where common sense goes to retire. Here's the strange part. If I ask you where a baseball is, you point. Easy, it's on the table. If I ask where the moon is, you can point to the sky and say, over there. But if I ask, where is the electron inside an atom? You'd think the answer should be even easier. After all, the atom is tiny. How many places could it be? And the answer, the honest, experimentally verified, cross-checked, argued over for a century answer is we don't know in the way you think we should. Not because we're bad at measuring, not because our microscopes aren't strong enough, but because where it is turns out to be the wrong kind of question. That's the paradox that gets us started. The most precise theory in all of science, the one that predicts the behavior of atoms to more decimal places than you have fingers, toes, and probably friends, refuses to tell you where the electron actually is before you look. Not, we haven't looked yet. Not, we could look if we had better tools. No, it says the electron does not have a definite position in the ordinary sense until an interaction happens. Now, if that doesn't make you slightly uncomfortable, you're not paying attention. Because everything in your daily life depends on objects having positions. Your coffee cup has a position. Your chair has a position. You have a position, hopefully a comfortable one. But the stuff those things are made of, the electrons and atoms underneath, don't play by that rule. It's like discovering that the bricks in your house don't actually have fixed locations, but somehow the house still stands. So what happens when you look inside an atom? And I don't mean look with your eyeball, because that would be a very short scientific career. I mean, what happens when you perform an experiment designed to find out where an electron is? You might imagine you just peek in there gently, like opening a door a crack. But nature doesn't do gentle at that scale. To see something, you have to interact with it. You have to bounce something off it light, usually. But light, when you zoom in far enough, isn't a smooth glow. It comes in little packets, photons, each one carrying a tiny kick of energy and momentum. So now your look is more like throwing a microscopic dodgeball at the electron and seeing where it goes. And the moment you do that, bam! The electron that was previously described by a kind of spread out cloud of possibilities suddenly gives you a definite answer. It hits here, not there. Here, a single point, a tiny dot on your detector. So you say, ah! It was there all along. We just didn't know it. But hold on. If you repeat the experiment, preparing the atom in exactly the same way, the next electron doesn't land in the same spot. Or the next, or the next. You get a pattern over time, a beautiful, predictable pattern, but each individual event is unpredictable. Fundamentally, not because of hidden dice we haven't found yet, but because the theory that works better than any other theory we have says that's just how it is. Before you look, the electron is described by a spread of possibilities. After you look, you get one actual outcome. And here's the kicker: the act of looking is not just revealing the answer. It's part of creating the conditions under which that answer becomes definite. That's the part that makes people start using words like observer and reality in very nervous ways, but we don't need mystical fog to make this weird. It's weird enough on its own in a clean, hard, experimental sense. You can build machines that rely on this fuzziness. Transistors, lasers, MRI scanners, they all work because electrons don't sit quietly like little marbles. They smear out in space in a way that's described by a mathematical object we call a wavefunction. And that wavefunction doesn't tell you what is. It tells you what might be and with what likelihood. So inside an atom, you don't have a little solar system with electrons orbiting like planets. That picture is charming and it got us somewhere for a while, but it's as misleading as drawing atoms as tiny billiard balls with smiley faces. What you really have is something more like a standing pattern of possibility, a vibrating cloud of maybe here, maybe there, held in place by the rules of quantum mechanics. And yet, this is important: when you do measure something, you always get a definite result. Never a blur, never half an electron. Always a crisp click in a detector, a sharp line in a spectrum. A specific energy, so the atom lives in this strange double life. Between measurements, it evolves smoothly, like a wave spreading and interfering with itself. During a measurement, it behaves like a particle, giving a single localized event. Wave and particle aren't two different things the electron switches between like outfits. They're two aspects of a deeper description that doesn't fit neatly into the categories your brain evolved to handle. And the real shocker, the thing that made some of the greatest physicists argue like cats in a bag, is that this isn't just a limitation of our knowledge. It seems to be built into the structure of reality. The world, at its most microscopic level, is not a collection of tiny solid things with definite properties waiting to be revealed. It's more like a set of evolving possibilities that only crystallize into facts when interactions occur. So when you look inside an atom, you don't just uncover what was already there. You participate in a process that forces nature to give a definite answer out of a menu of allowed ones. If that sounds like the universe is dodging the question, well, in a sense, it is. But it's dodging it with extraordinary consistency, mathematical precision, and experimental honesty. It never lies. It just refuses to answer in the classical language we keep trying to use. And that leaves us with a deliciously uncomfortable thought: the solid, definite world you experience might be built out of ingredients that, on their own, are anything but solid and definite. So the next natural question is, how do we even make sense of something that behaves like a spread-out wave of possibility one moment and a sharp, localized particle the next? What kind of picture, what kind of mental movie can we build that doesn't fall apart the second we push it too hard? So we've got this electron in an atom, not as a tiny bead whizzing around, but as a kind of spread out, maybe cloud. And already that's a tough pill, because your brain keeps trying to sneak the marble back in. It whispers, yeah, probability cloud, but really it's somewhere in there. That little voice is classical physics trying to sneak back into the room like a cat that got kicked out. Let's try something simpler. Forget atoms for a second. Imagine water waves in a bathtub. You slap the surface with your hand and ripples spread out. Those ripples aren't at one place, they're a pattern extended over space. If you put a cork on the water, the cork bobs up and down depending on where the wave is high or low. The wave tells you the chance the cork will be pushed upward at different places. Now in the quantum world, the electron has something like a wave, but not a water wave made of stuff sloshing around. It's a wave of possibility. The height of the wave at any point doesn't tell you how much electron is there. It tells you the chance that, if you go poking around with a measurement, that's where you'll catch it. So far so good. Weird, but manageable. But here's where nature grins at us. If this wave of possibility spreads out, it can do all the things waves do. It can interfere with itself. You know how two water waves can meet and make a bigger wave, or cancel each other out and leave the surface flat. Quantum waves do the same thing, except what's interfering isn't water height, it's probability. And this isn't just a metaphor. We can actually see it happen. Take electrons one at a time, just single, lonely electrons, and fire them at a barrier with two tiny slits in it. Behind the barrier is a screen that lights up when an electron hits. You'd think each electron would go through one slit or the other, like a tiny BB pellet. So over time you'd expect two piles on the screen, lined up with the slits. That's not what you get. You get a striped pattern, bright and dark bands, exactly like what you'd see with water waves going through two openings and interfering. But here's the part that makes you blink: the electrons go through one at a time. There's never more than one in the apparatus. And yet somehow each electron behaves like a wave that goes through both slits, interferes with itself, and then lands as a single dot. Each impact is a tiny, localized speck. But the pattern that builds up is a wave interference pattern. So what went through the slits? A particle, a wave. If you say particle, you can't explain the interference. If you say wave, you can't explain why the screen always records a single, sharp hit, never half an electron smeared out. So we say something more abstract. What goes through is a wave function, a mathematical object that evolves like a wave and predicts probabilities. When we finally detect the electron, that wave function gives us one concrete outcome. Now suppose you get clever. You say, ha! I'll put a detector at one slit and see which slit the electron really goes through. Perfectly reasonable. That's science. Don't just argue, measure. So you put a tiny detector by one slit. Now each electron either triggers the detector at slit A or it doesn't, meaning it must have gone through slit B. And when you do that, the interference pattern disappears. Not gradually, not kind of completely. You just get two boring piles like little BB pellets after all. Just the possibility of knowing which path the electron took is enough to destroy the wave interference. The wave of possibility that used to go through both slits now behaves as if it went through only one. Looking inside the atom, or inside this experiment, doesn't just reveal reality. It changes the very kind of reality that can happen. And please notice, this isn't about human consciousness or staring really hard. You can hook the detector up to a computer, turn off the screen, throw away the data. The interference is still gone. It's the physical interaction that matters, not your awareness. The universe doesn't care if you're impressed. What's happening is that when the electron interacts with the detector, the delicate wave of possibilities gets tangled up with the detector's state. Instead of one neat wave going through both slits, you now have different possibilities tied to different physical records in the world. And once those possibilities can, even in principle, be told apart, they stop interfering. Inside an atom, something like this is happening all the time. The electron's wave isn't just floating in empty space, it's shaped by the electric pull of the nucleus. Only certain standing wave patterns are stable, like the allowed notes on a violin string. That's why atoms have discrete energy levels, not because the electron chooses special orbits, but because only certain wave patterns fit without canceling themselves out. And here's the counterintuitive twist. The electron doesn't lose energy gradually as it moves around. It can only jump between these allowed patterns. When it jumps, it emits or absorbs a photon with exactly the right energy difference. That's why atoms give off those sharp spectral lines, little barcodes of light that tell you exactly what element you're looking at. So the structure of matter, the fact that chemistry works, that solids are solid, that your hand doesn't fall through the table, comes from these standing waves of possibility inside atoms. Not from tiny gears and hooks, but from allowed and forbidden patterns of quantum waves. Matter is stable not because electrons are little planets in tidy orbits, but because waves can only fit in certain ways. Now let's push it one step further, because this is where even seasoned physicists start pacing the room. Between measurements, the wave function evolves smoothly and predictably according to a neat little equation, the Schrödinger equation. It's calm, continuous, perfectly deterministic. If all you ever had was that equation, the universe would be one big, elegant, spreading wave of possibilities. But when a measurement happens, we don't see a spread of outcomes. We see one. The wave description seems to collapse from many possibilities to a single actuality. And here's the puzzle. The Schrödinger equation itself never mentions collapse. It just keeps evolving waves into other waves. So where does the single outcome come from? This is the part where different interpretations of quantum mechanics start to bloom like wildflowers. Some say the collapse is a real physical process we don't yet fully understand. Some say all outcomes happen, but in different branches of the universe. Some say the wavefunction is just a tool for calculating our knowledge. But here's the practical, working physicist attitude, which I have a lot of sympathy for. Shut up and calculate. Use the rules, they work spectacularly well. Build lasers, chips, atomic clocks. The universe clearly knows what it's doing, even if our language for describing it creaks and groans. Still, you can't help but feel the philosophical tremor underneath it all. Because if the basic ingredients of reality are these evolving clouds of possibility, and definite facts only appear in interactions, then reality isn't just a fixed stage where things happen. It's more like an ongoing process where possibilities continually crystallize into events. The atom isn't a tiny solar system. It's more like a tiny symphony of potential notes constantly shifting, interfering, and only occasionally forced to pick a single note when the rest of the world demands an answer. And that leads to a question that's both physical and almost existential. If the microscopic world is built from probabilities, superpositions, and interactions, how does the solid, definite world of our experience emerge so reliably? Why don't we see chairs in two places at once, or cats smeared across the living room like quantum fog? That's where the next layer of the story comes in, and it ties the fate of single atoms to the fact that you, right now, feel like a single, definite person sitting in one definite place in a very definite world. Okay? Now we're going to zoom out a little, but not so far that we lose the atom. Think of it more like stepping back from a painting. Up close, it's a mess of tiny brushstrokes. Step back, and suddenly there's a landscape. So far we've been obsessing over one electron, one atom, one delicate wave of possibility. And down there, the rules are slippery. Things spread out. They interfere. They don't have definite properties until something forces the issue. But you are not one electron. You are something like 128, 10, and 28, 10, 28 atoms all jostling together in a warm, wet, noisy environment. And that noise, that constant jiggling and bumping and exchanging of photons and vibrations, turns out to be the key to why the everyday world doesn't look like a blurry quantum dream. Here's the idea. A single electron's wave function can stay nicely spread out and coherent, like a clean musical note, as long as it's well isolated. But the moment it starts interacting with lots of other things, air molecules, light, nearby atoms, its delicate quantum phases get scrambled. The different possibilities get tangled up with the environment in incredibly complicated ways. This process has a fancy name, decoherence. But the basic idea is simple. Imagine you're trying to keep a perfectly synchronized group of dancers moving in step. That's like a coherent quantum wave. Now imagine a crowd of toddlers runs through them at random. Good luck keeping the choreography. When a quantum system interacts with its environment, the different branches of possibility effectively stop being able to interfere with each other. Not because interference is forbidden, but because the phase relationships become dispersed into trillions of environmental degrees of freedom. The information about which possibility leaked out into the world, and once that happens, the system starts to behave for all practical purposes like it has picked a definite state. The wave hasn't magically turned into a single classical reality in the equations, but from the point of view of any observer who is also part of that environment, the alternatives might as well be gone. They can no longer recombine and show interference. So the reason a chair doesn't sit in two places at once is not that quantum mechanics stops applying. It's that a chair is entangled with so many air molecules, photons, and internal vibrations that any superposition of chair here and chair there decoheres almost instantly, in times far shorter than you could ever notice. Inside an atom, coherence can survive long enough to produce interference patterns, discrete energy levels, tunneling, and all the other quantum tricks. But scale up, and the environment is constantly measuring everything all the time, whether we like it or not. In that sense, the classical world, the world of definite positions and solid objects, isn't the fundamental layer. It's what quantum mechanics looks like when you have huge numbers of particles entangled with an uncontrollable environment. Solidity is not basic, it's emergent. Now let's go back inside the atom one more time with this in mind. That electron cloud around the nucleus, that spread out wave of possibility, is not just a fuzzy picture. It's the reason atoms have size. If electrons were little point particles with definite orbits, they'd radiate energy and spiral into the nucleus in a tiny fraction of a second. Matter would collapse. No chemistry, no you. Instead, the electron's wave nature means it occupies a lowest energy standing wave, a kind of quantum ground note that can't shrink any further without increasing its momentum too much. There's a built-in trade-off, squeeze the position, and the momentum uncertainty grows. That's the uncertainty principle, not a statement about clumsy measurements, but about how wave-like things fundamentally behave. Because of that, atoms have a natural size. And because atoms have size, matter takes up space. And because electrons in neighboring atoms can't all pile into the same quantum states, thanks to another quantum rule, the Pauli exclusion principle, matter resists being compressed. That resistance is what you feel as the solidity of the table under your hand. So when you press your palm on the table, it's not little billiard balls pushing back. It's overlapping quantum wave functions rearranging themselves under strict quantum rules. Your hand doesn't fall through the table because doing so would require electrons to occupy forbidden states. Quantum mechanics says no, and the table feels solid. The everyday world, chairs, rocks, people, is a large-scale, averaged-out consequence of the strange rules we've been talking about. Underneath the apparent certainty is a seething, probabilistic dance, but it's so tightly choreographed by enormous numbers and constant interactions that it looks stable, definite, and dull in the best possible way. Now here's where things get really reflective. We like to think of reality as made of things, objects, stuff. But the deeper we look, the more it seems reality is made of events, interactions where possibilities turn into actual outcomes. The electron isn't a tiny bead with a continuous, well-defined history. It's something whose properties become definite in specific interactions, then dissolve back into evolving possibilities. Even Humpty space isn't truly empty. It's a stage where fields exist everywhere, and particles are excitations of those fields. The atom itself is mostly empty in the old, classical sense, tiny nucleus, diffuse electron cloud, but that humptiness is structured by quantum rules so strict that it gives rise to the rigidity of steel and the complexity of DNA. So when you look inside an atom, You're not just peering at a smaller version of the world, you know. You're looking at a layer where the categories of everyday language, position, path, object, start to blur. What's really there are patterns of possibility evolving according to mathematical rules of astonishing precision. And yet out of that abstract probabilistic machinery comes everything familiar. The colors you see come from electrons jumping between quantized energy levels. The chemistry in your brain, the signals in your nerves, the stability of your memories, all of it depends on those strange, non-classical rules. There's a kind of poetry in that. The certainty of your experience is built on top of uncertainty at a deeper level. The solid world is made from things that, in isolation, refuse to be pinned down. It's as if nature is telling us don't confuse the map with the territory, and don't expect the territory to be made of the same concepts your brain evolved to throw spears and peel fruit. The universe is under no obligation to be intuitively obvious, but it is under an obligation to be consistent. And quantum mechanics, as bizarre as it sounds when translated into everyday words, is internally consistent and experimentally flawless to a degree that borders on the miraculous. So something strange really does happen when you look inside an atom. You don't find tiny gears and clockwork. You find a world where possibility is as real as actuality, where waves of probability shape the structure of matter, and where the act of interaction helps define what is real in the first place. And somehow, through staggering numbers, relentless interactions, and the quiet work of decoherence, that strange, shimmering quantum world gives rise to this one, a world where you can sit in a chair, hold a cup of coffee, and wonder how on earth it's all possible. And the honest answer is, we don't fully know why the rules are this way, but we know with extraordinary confidence that they are. And every time we look deeper, nature doesn't get simpler. It gets subtler, more abstract, and, in a funny way, more beautiful. Not because it matches our expectations, but because it keeps surprising us while still making perfect sense on its own terms. It's not just that the atom is weird. It's that the weirdness isn't a bug. It's not a temporary glitch in our understanding. It's the feature. It's the way the world actually keeps its books. We started with a simple, almost childlike question: what happens when you look inside an atom? And the answer turned out not to be a smaller version of the everyday world, but something that forces us to rethink what we even mean by happens, inside, and uns, because down there at that scale, reality isn't a fixed script. It's more like a constantly updated draft, written in the language of probabilities. The wavefunction is not a list of facts. It's a catalog of potential stories the universe is prepared to tell, each with its own weight. And interactions, what we loosely call measurements, are the moments when one line gets inked in. Now here's the part that sneaks up on you. You are made of atoms, not metaphorically, not poetically, literally. Every cell in your body, every neuron firing in your brain, every molecule of air in your lungs is obeying these quantum rules. The same rules that say an electron can be in a superposition, that probabilities interfere like waves, that certainty emerges from a background of possibility. And yet you don't experience yourself as a blurry cloud of maybes. You feel definite. You remember yesterday, you plan for tomorrow, you have a sense of a continuous story called me. So somehow, out of this quantum fog, a classical narrative emerges. Not because the fog goes away, but because it organizes itself through staggering complexity and constant interaction into patterns that are stable enough to persist. Your brain is not a quantum computer in the psi sense, delicately maintaining superpositions of thoughts. It's more like a roaring, warm, wet, decohering machine where quantum rules set the stage, but classical patterns do the acting. Still, every one of those classical patterns rests on quantum foundations. The stability of molecules, the shapes of proteins, the behavior of semiconductors in the devices you're using right now, all of it depends on electrons not being tiny planets, but quantum objects with wave functions and exclusion principles and discrete energy levels. So when you hold a phone, you're holding a slab of controlled quantum behavior. Engineers don't need to argue about interpretations of the wave function to build it, but the reason it works is buried deep in the same strange rules we've been talking about. In that sense, the modern world is a monument to the fact that nature's weirdness is reliable. Now let's get a little more philosophical, but in a grounded way, not a stare into a crystal way. Classically, we imagine the universe as a big collection of things, each with properties, moving around in space and time, but quantum mechanics nudges us toward a slightly different picture. It suggests that what's fundamental might not be things, but relationships and interactions. The properties of a system aren't always sharply defined on their own. They become definite in specific context, in specific interactions with other systems. It's almost as if reality is less like a static photograph and more like an ongoing conversation. Each interaction is a line of dialogue where one possibility becomes actual, and that actual outcome influences what can happen next. Time, in this view, isn't just a parameter ticking along. It's the ordering of these events, these moments when the universe commits to particular outcomes. The future isn't a single pre-written script, nor is it a complete free-for-all. It's a branching structure of possibilities, constrained by the wavefunction's evolution and sculpted by interactions. And here's something I find deeply comforting about that. It means uncertainty is not just a limitation of our knowledge. It's built into the architecture of the world. The future is not fully determined in the classical, clockwork sense. There are real alternatives with real probabilities woven into the fabric of physics. That doesn't mean you can will electrons to behave differently or bend reality with your thoughts. The probabilities are precise and impersonal. But it does mean the universe is not a frozen block where everything was fixed from the beginning. There's genuine openness at the microscopic level, continuously resolving into the macroscopic story we experience. Now, we have to be careful. It's easy to take words like observer and measurement and wander off into mystical territory. But the lesson from physics isn't that the mind creates reality. Its subtler and, in my opinion, more interesting physical interactions are what make certain properties definite. Observers are just particularly complicated physical systems that keep records. You, as a conscious being, are part of this web of interactions. When you look at the world, photons scatter into your eyes, signals propagate through neurons, memories form. You become entangled in the broad physical sense with what you observe. You are not outside the universe, peeking in. You are one of the places where the universe is happening. So looking inside an atom is not just an abstract scientific act. It's the universe, through a very complicated arrangement of atoms called a person and some instruments, interacting with another arrangement of atoms and forcing a question to be answered in a definite way. That's a pretty wild thought, the cosmos examining itself at the level where its own rules are most exposed. And the more carefully we ask, the stranger and more precise the answers become. We get equations that predict magnetic moments to 12 decimal places, energy levels to absurd accuracy. And those same equations tell us to give up the idea that particles always have definite positions and paths. Nature is telling us, very politely but very firmly, your everyday concepts are approximations. Useful ones, beautiful ones, but not the final story. There's a kind of humility in that. Every time in history we thought we'd reached the bedrock, solid atoms, then nuclei, then protons and neutrons, then quarks and fields, the universe said, good guess. Now look closer. And closer has always meant stranger, more abstract, and more mathematical. But also, in a funny way, more unified. The same quantum principles that govern an electron in a hydrogen atom also govern the fusion in the sun, the behavior of neutron stars, the chemistry of life. The rules are universal. The weirdness is not confined to the lab, it's the operating system of reality. So when you step back and look at the big picture, the strangeness inside the atom is not an isolated curiosity. It's the foundation of structure, complexity, and even the possibility of stable matter. If electrons behaved like classical particles, atoms wouldn't exist in their current form. If quantum probabilities didn't interfere, chemistry would be unrecognizable. If the exclusion principle didn't hold, matter might collapse into something unlivable. Your existence depends on quantum mechanics being weird in exactly the way it is. That, to me, is the most astonishing part. The fact that a set of rules that sound like they belong in a surrealist novel, particles going through two slits at once, properties undefined until interaction, probabilities behaving like waves, turn out to be the precise, dependable machinery that allows stars to shine and brains to think. We started with the question of what happens when you look inside an atom. The answer is, you find that the act of looking is part of the story. You find that reality at small scales is not a collection of solid certainties, but a structured web of possibilities. You find that the definite world emerges from this deeper layer through interaction, entanglement, and decoherence. And if you let that really sink in, it changes the flavor of how you see everything else. The chair you're sitting on isn't just there in the simple naive sense. It's a stable pattern arising from quantum fields, held together by allowed energy states and exclusion principles. The light hitting your eyes is made of photons emitted when electrons jump between quantized levels. The sense of touch in your fingertips is electromagnetic repulsion between electron clouds. The ordinary is built from the extraordinary. And the fact that we, collections of atoms obeying these same laws, can figure this out write equations about it, build experiments to test it, and then sit back and feel a little dizzy at the implications, well, that might be the strangest and most wonderful part of all, because it means the universe is not only stranger than we imagine, it's stranger than we can imagine, and yet, through mathematics, experiment, and a lot of stubborn curiosity, we can still learn how it works. We may never get a picture that feels as comfortable as little balls flying around in neat paths. But we get something better, a set of principles that, while conceptually unsettling, are breathtakingly accurate and deeply connected to everything we see. So the next time you hear atom and picture a tiny solar system, remember, it's not a miniature clockwork, it's a humming, probabilistic structure where reality is continually being negotiated through interaction. And somehow, out of that negotiation, comes a world solid enough to walk on, bright enough to see, and rich enough for a bunch of atoms to sit around wondering how the whole improbable thing works at all.